Hi, this is my lecture on chapter 2. The chapter 2 is entitled Describing Data with Numerical Measures, and the following provides a summary of what we will cover in this lecture. This lecture will cover various ways to summarize data, specifically summarize two different aspects of the data that you have. One, the measure of center or central tendency. So you have a data on, let's say, people's age in the United States. You went off and you collected age information from 1,000 people in the United States. The measure of center gives, well, what's the average? What would we expect? What is the typical age of these people, 1,000 people we collected data on? And there's basically 4 ways we're going to learn about: mean, median, and mode. And then we're going to also learn how to take weighted averages. The next is the measure of variability. How spread out is the data? Again, we collect data on 1,000 people, data on age of 1,000 people in the United States, and we want to measure how widespread the age is of these 1,000 people. Does it go from 30 to 34? That's not very widespread, very tight. The quote unquote distribution of age among these 1,000 people, it's very tight between 33 and 34, whatever I said. Or is it between 1 to 105? That's pretty widespread. Okay, that means the data has wide variability, while the first one is very narrow variability. 3 measures of variability is range, variance, and standard deviation. We will then turn to Chebyshev or Chevyshev's, whatever, so 2 different ways of spelling the dude's name. Some Russian dude, his theorem. Okay, and Chebyshev's theorem, I'll explain what that is, and the empirical rule. That is a variant of Chebyshev's theorem, only applied when you have basically bell-shaped, or what we call normally distributed data, bell-shaped curve data. Lastly, we're going to talk about measure of relative standing, where you are, meaning where one data point is relative to the other data points. One thing we're going to learn about is the z-score. Next is percentage, quartiles, and then the 5-number summary and the box plot. Okay, so now what we're going to do is go through the measure of center or central tendency. Let me clear this, move on. As I kind of alluded to in the summary or overview of this chapter, the measure of center or central tendency, this is the center of the distribution. What I mean by that, for example, as I stated, let's say we have an example. Screwing things up. All right. Suppose we collect age information, the age of 1,000 people in the United States. Then your boss will say, what's the average? What he's basically or she's basically asking for is, what's the middle point of this data? What is the measure of center or the central tendency? Okay. And when your boss asks for what's the average, that person is usually asking for the mean. right? But as I alluded to earlier, there's 3 other ways we can measure center that we're going to go over in this class. Okay. So what is the mean? The first one we're going to go over is the mean. The mean, we use the following, okay? To distinguish from the mean of the sample versus the mean of the population, we are going to use the following, okay? The sample mean, we use X bar. This is the symbol we use for the sample mean, okay? And here, the formula is sum of xi from 1 to n divided by n, okay? This is xi, where xi is the ith data. Okay, so for example, let's say we collected data of age of 10 people in the United States. So we have n is equal to 10, or sample the size is 10. Oh, wait, n is sample size. Okay, so n is 10, or 10 data points are 5, 7, 8, 12, 22, 23, 1, 2, 3, 6. These are 10 age data. We have a 5-year-old, a 7-year-old, 8-year-old, 12-year-old, so on and so forth, 99-year-old, and a 3-year-old. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. To calculate the sample mean, this is equal to 5 plus 7 plus 8 plus 12 plus, oops, let me erase that. Plus 22 plus 23 plus 24 plus 45 plus 99 plus 3, all of this divided by 10. And that's how you would calculate it, okay? There is an example in the book, and my notes as well. So if you want to do another calculation. All right. What about population mean? Okay. Population mean, we use this, the symbol mu. It looks like a U, fancy U, and it's stated as said as mu. Okay, and mu is equal to the sum I is equal to 1 to capital N. Okay, xi divided by capital N. Okay, and where capital N is number of observations in population. Okay, so for example, if we are going to measure example, we were able to collect data on the age of everybody in the United States. Then and your boss says, well, what's the average age of everybody in the United States? And the United States is, say, our population of interest. Then you would get everybody in the United States, sum them up, and n would equal to whatever, 350 million, whatever the number of people in the United States. Okay. So this is basically the sample mean. That's the formula, and this population mean, that is the formula. Okay. In Excel, okay, Excel formula, and I'll use that after I introduce mean, median, and mode and whatnot. Excel formula is just average. And then you put data inside. You put average, open parentheses, put data inside, close parentheses, and that will calculate the mean. All right, I'm going to erase this, and now we're going into the median. We're going to talk about the median. The median is denoted by n, okay? We use the letter M to denote median of a set of data points, n measurements. Sometimes people say observations, sometimes people say data points, other people say measurements, okay? This is the value of X that falls in the middle position when the measurements are ordered from smallest to largest, okay? So when we order the data from smallest to largest, the midpoint, that's considered the median. Slightly different from the mean, okay? And I will show you that. This median eliminates the noise associated with extreme values. The mean will be affected by quote-unquote outliers or extreme values, and I will show you that later. If you had an odd number of observations, then the median is the middle value. If you had an even number of observations, the median is the middle or the average of the two middle values. Okay, so for example, let's say we collected age of 3 people. So we have 3, 7, and 9. And someone says, well, what's the median? This is the median, 7. We had odd number of observations, 3. The middle one is considered the median. So now let's say we had the age of 4 people. We have 3, 7, 9, and 10. What is the median? It is the average of these two. So what you would have to do is put 7 plus 9 divided by 2, which should be 8. Okay. That's the median. To calculate the median in Excel, the Excel formula is median. Okay. And then you put in the data, and that's it. That's how you calculate the median in Excel. Okay. The next one we're going to do is called the mode. So let me copy that in for you. Okay. Erase this. Okay. Mode is another way of trying to locate the middle of the distribution. And the way we look for the middle using mode is, what is the value of X that happens the most? So what do I mean by that? Okay, so let's give you an example. Okay. So let's suppose we have the age, we collected age of like certain number of people. So we have a 3-year-old, a 4-year-old, 5-year-old, 5-year-old, 7-year-old, 5-year-old, 80-year-old, 77-year-old, and 105-year-old. The mode would say, well, what's the data? What's the value that happens the most? And we see here, we have 1, 2, 3 5-year-olds. So the mode will equal to 5. Okay. And then you can look at the example for birth rates. All right. If you look at a frequency distribution, you have some data on X, and you have like frequency or relative frequency graph. It shows bars, right? Like this, the bar graph. This is the mode, because that's the one that happens the most. The mode is generally used to describe large data sets where the mean and the median are used for both large and small data sets. Okay, so mode is not something we generally use for small data sets, but it's possible. Okay, you can calculate it. Physically calculating that isn't hard. Okay, the data can have multiple modes. If you have more, so you could have age data right here, and if you have another 2 4-year-olds, the mode will be 5 and 4. In that case, we would have a bimodal distribution. Bimodal distribution, meaning the data has exactly 2 modes. Now, if you have more than 2 modes, it's called a multimodal distribution. Now, if you see a situation like that where you have a bimodal or multimodal distribution, it may mean that you have 2 groups that are kind of merged together, and you think it's one group, and in fact, they're 2 distinct different groups. For example, if we have a large set of data and we didn't separate, men from women, you would likely see a bimodal distribution for weight and height. Women are generally a little shorter than men, so you would have the average weight of men being one and average women being another. And the height and the weight would be the same. Men are generally heavier than women, so you could have bimodal distribution of weight or even height or both. In this situation, you look at the data and you see that you have a bimodal distribution. It'll allow you to dig deeper in the data and try to figure out, is it possible that I accidentally put two different groups, such as men and women, and consider them one group? And maybe you dig deeper and you find out you did that, and you could separate them out into 2 different groups. It's a way to try to figure something like that out. Investigate the data. For mode, there are 2 formulas in Excel. Okay. Excel has 2 formulas. And the first one that I would suggest is mode dot, oops, let me MULT, and the other one is mode dot SNGL. Put data inside and put data inside. There's really no use of using this one. I really didn't know about this one until recently. So if you look at my notes, I only give you this one. Mode.sngl. If there's 2 modes, mode.sngl would only give you the lowest mode. Okay. Gives you the lower value mode. So for example, if you had 1, 2, 3 4-year-olds and 1, 2, 3 5-year-olds, so we had a mode of 5 and 4, mode.mult, and you put data in, will give you both 5 and 4. mode.sngl and you put data in, you would only get the 4. So really, there's no real use to use this mode.sngl single. Always use the mode.mult. Okay. All right. So now what I'm going to do is, before we talk about weighted means, we'll go to Excel and practice using mean, median, mode in Excel. Okay. Using those formulas. All right. So let's do this. And we'll clear this. I'm going to new share screen 1. Oh, then no, let's just stop sharing. Okay. So I'm sharing the Excel file. Let me blow it up. All right. So let's just create some data. And let's have observations. Let's say there's several observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay, let's put 10 right now. And let's say it's the age information. So we have like a 9-year-old, an 80-year-old, a 10-year-old, 12-year-old, 35-year-old, 43-year-old, 99-year-old, 19-year-old, 9-year-old, and 8-year-old. Okay. So suppose we have this type of information data. Okay. So to calculate the mean, we have the easy way and the hard way of calculating this. The hard way would be to calculate using the formula, and this would equal to the sum. You have to sum all of the ages. Okay. Highlight all the cells, divided by how many observations do we have? We have 10. Let's just divide by 10. Enter. And this is the mean. The easy way of calculating the mean is equal to average, open parentheses, highlight and drag all the data in, close parentheses, and you should get the same information. Okay. Now let's calculate the median. For the median, they say, well, golly, you should sort this first. Okay, so let's sort it. Data, you go to data and sort. Nah, just continue, sort. And we sorted the data. It went 8, 8, 9, 9, so it goes like this. Okay, from lowest to highest. The median is, if you have even, it's the average of the middle two. Well, what's the middle two? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the middle two is these two guys. So the median is equal to average of the middle two, which is the 5th and 6th observations. Highlight those two, close parentheses, and it's 11. And of course, the easy way of doing the median is just use the median formula. Median, open parentheses, highlight everything, close parentheses, and it is 11. Okay, now let's do mode. Mode, there's no real formula. I mean, there's an Excel formula, but there's no mathematical formula. You just kind of look at this and look for what the mode is, what happens the most. And you got 8 and 9. So you have a mode of 8 and 9. Those are the two this is a bimodal distribution. Okay. And then you could just do that easy way, mode dot MULT. So you see that when I start typing in mode, all the possible formula that starts with MOD pops up. And we said, oh, we wanted to use .MULT, open parentheses, put in the data, close parentheses, and you can see how it gives us both like this, 8 and 9. Okay, we're done with this. I showed you an example of how to use mean, median, mode, how to calculate by hand, and also how to calculate using Excel formulas. Now let's move on. And now we're going to talk about weighted mean. So I'm going to share the whiteboard. So what is weighted mean? Weighted mean. It's a mean is computed by giving each observation a weight that reflects the relative importance. Okay. The choice of the weight really depends on what makes sense. For example, for weighted GPA, the weights might be the number of credits earned in each class. Okay, so what is the formula for weighted mean? Let me give you that first mathematical formula, and then we'll do an example. Okay. So the formula for weighted mean is equal to, let's use X bar as the mean, but we know it's the weighted mean for right now. This is the sum of I to 1 to n, Wi, xi, the weight of the ith person, ith observation times the value of the ith observation divided by the sum, I equals 1 to n, of Wi, divided by the sum of the weights. Another way of writing this out is the sum, I equals 1 to n, Wi over sum of Wi, I equals 1 to n, times xi. These two formulas are identical mathematically, just two different ways of presenting it. One says, let's just, this one here says, okay, let me, you know what? I should write out what these things are. Okay. Where xi is ith value, Wi is weight for ith observation. Weight for the ith observation. Okay. All right. If we want to calculate this for population, this is actually for the sample, because we have xi, sample. For population, sample. For population, you replace xi with mu. This would be for population. All right. All right. Now let's talk about this formula. Here, this one, again, this and this is identical. Here, this one is just saying, okay, for each ith value, we're going to multiply it by the weight. We're going to sum them all up, the weighted sum for each I, and then divide it by the sum of all the weights. Here we're saying, okay, let's take the relative weight. The Wi is the ith weight divided by the sum of the weights. So this is relative, how important I is, ith weight is, relative everybody else's, and multiply that by ith value, and then you sum them all up. This might sound confusing, but we're going to do it, okay? All right. Let's do an example. Suppose there's an individual and he took physics, super hard, super honors physics, and he took cooking. Okay, 2 classes. Physics, he got an A. Cooking got a D. An A is equivalent to a 4.0, and a D is equivalent to 1. So then someone's like, okay, what's this person's GPA? Okay. And then someone would say, okay, well, the GPA, the grade point average, is equal to 4 plus 1 divided by 2. 4, 5 divided by 2 is equal to 3.5. Okay. Oh, no. 2.5. Wish I could do math. 2.5. Okay. Well, then let's say, this person's like, the student's like, wait a minute, this is not fair. Physics is a 4-unit class. Cooking is a 1-unit class. Is it fair to give the A the same importance as cooking when physics has 4 units, meaning it's like 4 times harder? One way of looking at it is 4 times harder than cooking. So the student's like, I think we should calculate it differently. Okay, specifically, the student is like, think about it this way. For this semester, I took a total of 5 units. Okay. And it's like I have an A for unit 1, an A for unit 2, an A for unit 3, an A for unit 4, and a D for unit 5. Okay. This person's like, I think I have 5 units. 1, 2, 3, 4, 5. 4 of the units in this semester is an A, and the 5th is a D. 1A is a 4, and a D is a 1. So to calculate my GPA, it should be 4 plus 4 plus 4 plus 4 plus 1 divided by 1, 2, 3, 4, 5 divided by 5. And this would equal to, let me do it in Excel real quick, because I'm horrible at this. Three 3.4. How? It's 17 divided by 5, 3.4. This looks a lot better than a 2.5. Okay, so wait. 4 plus 4 plus 4 plus 1. This has nothing to do with this or this, does it? It does. How? Let me erase this. Let me rewrite it differently. Okay. We could group these 4s. And we could say that's 4 times 4 plus 1 times 1 divided by 5. Or another way to write this is we could separate these and say 4 times 4 divided by 5 plus 1 times 1 divided by 5, or 4, 5 times 4 plus 1, 5 times 1. Okay. This is like this way right here. 4, this is a weight. This is X. This is a weight. A 1 is a weight. And this is X. The weight of 4, because we had 4 units, times the grade is an A of 4, plus, okay? 1 is the weight times the grade of 1, divided by the sum of all the weights, which is sum of weights is 4 plus 1, which is 5. 5. Here, this way is like this. The weight for physics divided by the total weight for fifth times the value, which is an A's value of 4, plus 1/5. That is the weight is 1 for cooking, divided by 5 is the total weight, times 1, which is the D. And you add these two up. Okay. This is the intuition behind weighted average. All right. And to calculate weighted average, let's go to Excel and let's just do one. I'm going to clear this and share Excel. Open up another tab. Let's put in some data and let's just calculate. Okay. All right. Data. What data should I put in? Well, I don't know. Let's just put in grades, okay? Let's just pick up some grades. So the student took physics, took cooking, took math. Okay, those are the let's say 3 classes. And these are the class names. The student also took what we need to give the units. Let's say this is 4, 1, and 3. Okay. And then center. And then the grade. And student got an A, so 4. Cooking was a D, so 1. And math got a B, so 3. Let's just do it that way. All right. Okay, so total units. This is equal to sum, open parentheses, highlight all the data, close parentheses. That's the total units for the student for this one semester. So now let's calculate the simple average. Okay. So someone just says, hey, what's this person's GPA? Well, what's the average of a 4, a 1, and a 3? Equal to average. That's the mean. Highlight all the data. Close. 2.67. To not show so many decimals, go up here. And it kills the decimals. If you press this button, it adds a lot more decimals. Let's just do 2. Weighted average. Okay. Weighted average, we're going to use the units as weights. So the first thing we have to do, this is our weights, that's our W. And this is like our X. So the first thing we need to do is calculate W times X, which is equal to 4 times 4. Let's do that for all of the classes. Equal to 1 times 1. And we could copy the formula down, Control C, go down to where you want to copy to, Control V, click on it to make sure you copied the formula correctly. Okay. So that's WX, that's like a numerator, that's like our numerator. And our denominator, and so what we need to do to fully get the numerator is sum it equal to sum. And to get the weighted average, it is this dude, 26, divided by 8. Okay. And you could see if you weigh the grades by the number of units they took, the GPA is different. All right. While we're here, I forgot to talk about in the mean, median, mode example, what happens basically if you have an outlier or very extreme data, how the mean is affected by that, but the median is not. So let's talk about that right now. Let's create some data. Let's just say we collected data of income in the United States. So we collected data of like, I don't know, and we have like someone who makes 50,000, someone who makes 45,000, someone who makes 75,000, another person makes 120,000, someone who makes 35,000, another person who makes 65,000, someone else makes 78,000. Okay, so we have a bunch of people and their income. I'm going to put the comma. Okay. And then we have one super CEO who makes 15 million a year. Okay, so let's suppose we collected data on income in the, wage or income in the United States. We have people who makes 50, 40, 75,000, 120,000. Maybe this is like a medical doctor, a low-level medical doctor, and someone who makes 15 million a year. Okay. If you calculate the mean, that's average, open parentheses, highlight all the data point, close parentheses, you will have calculated the average income in the United States to be 1.7, 1,722,444,000. The median, let's see, is that different? 65,000. What looks more reasonable in terms of reflection of this data? If you look at the data, you got a bunch of people hovering, below 100,000. Yeah, there's this one dude here and one dude here, but most people are making less than 100,000. So if someone asks, well, what should we expect? Does it make more sense that we'll have 1.7 million or 65,000? The average is skewed by this very large extreme data, like whatever Jeff Bezos income, whatever that is, 15 million. Okay, Jeff Bezos is probably more like this, okay, per year. Does that even, now it's even more ridiculous. Now people, if someone asks you, well, what's the typical income of people in the United States? It's $166 million a year. Yeah, we all know that doesn't make sense. It was just the data is the distribution is skewed, or the center is skewed by this one extremely large number. The median, you could see, is unaffected by this really large number. No matter how big I make it, the median stays the same at 65,000. Okay. That's why for most of our analyses, what I like to do is calculate not just the mean or the average. Most people, calculate the average, but calculate the median, mode as well. Mean, median, mode. I don't really depend too much on the mode, but I like to see if we have issues with bimodal issues, as I discussed before. And median is very good to calculate, because if you see this type of difference between the mean and the median, you know the data is skewed, or you have some weird observation at the high end. Okay. If you have something like this, sorry. you have something like this, no. Let's say something like that, negative. Oops. Let's get that negative. Format, number. We use negative signs. Okay. And then mean is extremely negative number. It looks like we have an extreme outlier at the left-hand side of the district, some extremely low number. Okay. When the mean is less than the median, that means the outlier is extremely low. When the mean is greater than the median, then potentially there is an outlier and it is extremely high. Depends on how big the difference is. Okay, let's move on, go back to the whiteboard. Okay, so we talked about the mean, median, mode, and we talked about weighted average. And now we're going to go to measures of variability. Okay, so let's start talking about that. The measures of variability. This section focuses on the variability, dispersion, or noise in the data, distribution of data, and the measure of and measures of central location, distribution of data. Okay. Data sets may have the same center, but look different because of the way the numbers are spread out from the center. What do I mean by that? Okay, let's suppose we have the following. With two relative frequency distributions or histogram. Okay, and this is like age in US, age in US. And let's say someone saw this. Okay, 33, 34, 35. And someone else collected data and found this. Here, oh, it's kind of slanted, Leaning Tower Pisa. This is 34, and then it goes from like 25 and 55 or something like that. Both, let's say, has the mean or the center right at 34, right here. Okay. However, this data is very tightly, distribution of the data here is very tight, meaning all the data is either 33, 34, or 35. Here, the data is more spread out from 25 to 55. Okay. So even though both of them have the same measure of central location, here we have a narrow distribution or tight distribution. And here we have a widespread distribution, wider spread distribution. Okay. All right, let's move on. And let me clear this. More from the notes. Read this one. We didn't talk about the example. Look it up in the notes. Okay. Variability is also a very important characteristic of the data. For example, if you're making bolts, and these bolts must be 12 millimeters in diameter, extreme variation in the bolts, meaning like your manufacturing process makes bolts from 4 millimeter to 28 millimeters all over the place. That means you got to throw away all of them that are not 12. But if you have very tight distribution, so your bolt is from 11.99 to 12.0001 millimeter, then likely you're not going to throw away a lot of bolts, maybe no bolts, because those are all close enough in terms of your tolerance for your customers. However, there are times where you may want large variability. Suppose you want to measure the quality of accountants and you give an exam. You want an exam. Okay. Oops, not example. You want an exam with variability in the grade. You don't want everybody to get A's because then you can't tell who's a good accountant and who's a bad accountant. You want to give a test that some people get A's, some people get F's. Okay. All right. With that out of the way, let's talk about various ways of measuring variability. And the first one is called range. Range, you use R for range, of the data set of N observations or measurement is basically the difference between the largest and the smallest measurement. Formula is pretty easy. It's just highest minus lowest. Okay. It's a very simple measure of variability, but it's very sensitive to the extreme values or outliers in the data set. Okay. For Excel, you would have to use a combination of two formulas. It would be max, you put data in, minus min, put the data in. So once you put the data in, max will find the max, minus min will find the min. And the difference is the range. Okay. All right, the next one we're going to talk about is variance. Okay. Oh, lost a little. All right, that's how it's I lost all the little circles and squares. Okay, variance. It's sometimes called the second moment. Okay. First moment is actually the mean. Measure of variability that utilizes all of the data. This is the measure of variability that most people will depend on. Well, actually, it's a square, it's the standard deviation, which is the square root of this. And it's basically, variance is based on the difference between the value of each observation and the mean, the sample mean or the population mean. You get that difference, you calculate it for each observation, and then you square it. Then you take the average of that by summing them all up and dividing it by n, or in the sample variance case, n minus 1. I'll write out the formula. It can be useful in comparing the variability of two or more variables, and it has to be greater than or equal to 0. The problem with variance is that the variance units are in terms of square of the original units. What does that mean? If we're collecting data on age of people in the United States, variance is age squared. Okay. And here is if the original measure are in inches, the variance is expressed in squared inches. All right, so what does the formula look like for variance? Okay. Looks like the following. For the population variance, okay, we use sigma squared for population variance, and that is equal to the sum I equal to 1 to n xi minus mu squared. The difference from ith observation's value minus the average, you square that, and you take the average by summing them up and dividing it by n. Okay, for the sample variance, okay, this is s squared, and this is equal to the sum of I equals 1 to little n xi minus x bar squared. Okay, you sum them all and divide it by n minus 1. Why minus n minus 1? Why do we subtract 1 in sample and not population? It has something to do with something called a degree of freedom that you haven't been taught yet. We will learn that in a few chapters from now. So don't worry about it and just say that, the teacher or God or nature or whatever you believe in says it should be n minus 1 for now. Okay? All right. Let me move on. I'm going to clear this. Clear. And now let's talk about the standard deviation. Okay, kind of alluded to this earlier. Standard deviation. It's just the square root of the variance. Standard deviation is more appealing to use, and most people use this. Why? Why do they use this instead of the variance? It's because it has the same units as the original measurement. So if, again, we're measuring things in inches, then standard deviation is also in inches. We're measuring things like age of people in the United States, and the standard deviation is also in years, not years squared. All right. So how do you calculate standard deviation? Okay. For the sample, the standard deviation is S, and it's just S squared, the variance square rooted. For the population, same thing. It's just sigma. And this is sigma squared, which is the variance of the population, square rooted. That's all it is. All right. So from here, what I'm going to do, oh, well, let me give you this, the formulas, and then we'll go to Excel formulas. Okay. So the variance, and then we have population. This is VAR dot P, and then you put data in. For the sample, it's just VAR dot S, and you put data in. Most of the time, we're going to use the sample. And then standard deviation, population, just VAR dot S, and you put data in. And for the sample, it just, oops, I gave you the, oopsie daisy, getting old. For the standard deviation, it's STDEV dot P, and you put the data in. That's a dot. For the sample, STDEV dot S, and then you put the data in. Okay. So those are the formulas. All right. So what we are going to do is use Excel to calculate the standard deviation and variance, the quote unquote hard way, using the the mathematical formula. And then we're going to calculate the easy way using Excel formula. So let me share Excel. All right, let's make some data. Okay, let's say 1, 2 observations. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. And then the x's, I don't know, let's say it's age, x, this is age. We have about 33, 34. Oh, no. Okay, so that's our age. That's our x's. Okay. So then to calculate the variance of this sample, we'll assume this is a sample of people in the United States and not the population. To calculate that, we need first the mean. We need the average. Mean is equal to average. Highlight all the data, close the parentheses, and that's the average age of the people in our sample. And then what I have to calculate is xi minus x bar, the difference between each of these and the mean. Okay, so that is equal to xi minus the mean. And I want to scroll this formula down, so I have to anchor the mean. And remember how to anchor? Press $, B, $14. So then if I copy and paste the formula down, I'm going to use the little square. Okay. And check each one. Yeah, it uses this minus that. Check one down here. This minus that. Yep, did it correctly. Okay. So these are xi minus x bar. And then I got to square it. Remember, we got to square it to the little caret. That means to the 2 power. Okay, that's squared. In order to do that, you just do equal to this multiplied by itself, or you could do this to the, which is shift 6, the little caret, squared. Okay. I'm going to copy the formula and paste it into this area. Make sure the formula is correct. Click on a random. Yeah. Squaring that. Squaring it. Yep. Okay. Squaring it. Okay. And then what I have to do is sum these guys up and divide it by the number of observations we have, 10 minus 1. Okay, so I'm going to do that in one cell. So the variance, that is equal to the sum of all of these divided by 10 minus 1, which is 9. There's a variance. So that's how you do it if you didn't know the variance formula. And then we have standard deviation. This is equal to this to the 0.5, or the square root. That's how you do square root, to the half power. And it's this. All right. Well, let's suppose I know Excel. Then it's equal to VAR dot S for sample, open parentheses, put in all the data, not the age, just these guys, the data points, close parentheses, got the same number. Square root, standard deviation is just square root of that, but we have its own separate formula, STDEV dot S, open parentheses, highlight all the data, close parentheses, and you see you get the same number. Two different ways to do the same thing. Whatever you know how to do, use that to do well in the class. And there's probably 10 other ways to do this as well. All right, let's go back to the whiteboard. So I showed you the mean, median, mode, weighted average, range, variance, standard deviation. And now what we're going to do is go to Chebyshev's formula or theorem, Chebyshev's theorem. Clear this. Okay. What does Chebyshev say? So this is under the subheading, Understanding and Interpreting the Standard Deviation. A Russian mathematician, his name was Chebyshev. That's how you say it in the book. Other spellings is Chebyshev, like that. Gives you the lower bound of the percentage, fraction, or proportion of measurements, all of these being interchangeable, that you can expect to find to fall within a certain interval. Okay. So what he basically said is the following. It applies to any sets of measures, sample or population, large or small, mound shape or skewed. He says, look, I don't care what the distribution is. This applies to anything. And I give you the most conservative measurement. Specifically, what he says is given some number k, and this k has to be greater than 0, greater than 1, and a set of data points, n. Then he says at least this formula, 1 minus 1 divided by k squared. Okay, look, this is, let me rewrite this. This is wrong. Okay. This is 1 minus 1 over k squared. Okay. This much of the data point will lie within k standard deviations of the mean. So k, measuring how many standard deviations you are from the mean, you put boundaries, and how much of the data will lie within these boundaries? This much right here. Okay. So we have a distribution. Okay. Yeah, I'm going to make it smooth. Let's say we have a distribution that looks like this. And here's some variable x. And this is the relative frequency. And let's say this right here somewhere, I don't know, right here, we have the mean. Okay. And let's suppose we cut the data up, equal distance from the mean. Okay. So let's say right here and right here. Okay. Where this is x bar minus k times s, and this is x bar plus k times s. Okay. Where k is greater than 1, s is equal to standard deviation. Okay. Then within this area right here, Chebyshev says 1 minus 1 over k squared of the data will be inside these two boundaries right here. Okay. For example, okay, if k is equal to 2, then 1 minus 1 over 2 squared is 4. So 1/4, 1 minus 1/4, or 75% of data is 2 standard deviation from mean. Okay. If k is equal to, well, let me just copy this. If k is equal to 3, okay, that 89% of the data will be within 3 standard deviations from the mean. And if k is equal to 4, 94% of the data is within 4 standard deviation from the mean. Okay, that's what Chebyshev said. And Chebyshev's formula is very powerful, or theorem, because it doesn't matter if it's bell-shaped like this. It doesn't matter if the distribution looks like this. It doesn't matter if the distribution looks like this, or if the distribution looks like this. It applies to all the possible distributions. Okay, it gives you a very conservative measurement. The next one, what we're going to do is learn about empirical rule, which only applies to bell-shaped distributions. So we'll clear this. It's another rule describing the variability of the data set and does not work for all data sets. It only works if the data is quote unquote piled up or are familiar mound-shaped or bell-shaped. So this one will only work if your data looks kind of like this. Okay. So if you have this type of situation, okay, the empirical rule says the following. Okay. Rule says the following. 68% of data is within 1 standard deviation from mean. This is different from Chebyshev, okay? Chev said 0, at least 0%. At least none of the data is within 1 standard deviation from the mean. The empirical rule says 95% of data is within 2 standard deviation from mean, while Chebyshev said at least 75%. So you could see if you have mound shape, more of the data is within the barriers compared to if you don't have mound shape. Chebyshev is saying, look, man, mine applies to everything. And I'm saying the worst case scenario is 75%, but it's at least 75%. And then empirical rule says 99.7% of data is within 3 standard deviation from mean, where S is standard deviation. And again, Chebyshev said at least 89%. Okay. Okay, so that's basically empirical rule. Empirical rule only applies to situations where you have bell-shaped curve, you know, the classic piled up mound-shaped curve. And in these situations, if you have something like that, you know more the data is closer to the middle compared to, say, Chebyshev's theorem says Mine applies everywhere and at least a certain percentage. Okay. All right, let's move on. The next thing I want to say real quickly is the following. The range, using the range to approximate the standard deviation. This is back in the days when people didn't have computers and cell phones and whatnot. The range is approximately equal to 4 times the standard deviation. So the standard deviation is range divided by 4. So when would you use this? If you had no choice and you want a really rough guess of what the standard deviation is, you get the max and the min divided by 4, and you could kind of approximate the standard deviation. This doesn't work always, but it's close enough for whatever we need to do. And then you'll see an example 2.9 in the book where it calculates the rough standard deviation using this is 1.5, while the actual standard deviation is 2.39. So yeah, is that close enough? You could say whether it's close enough or not. I don't think it is, but it's one way of roughly calculating the spread when you don't have any way of calculating with like cell phones or computers. All right. Now from here, we're going to get to the measurement of relative standing. We'll clear this. Okay. And the first one we're going to talk about is z-score. Basically, what is the measurement relative standing? What is this section about? Sometimes you want to know the position of one observation relative to others in the data set. One measure is called the z-score, and it uses the mean and the standard deviation of the data set for this measure of relative standing. And it basically shows you how far some observation is away from the mean, or how far it is from the mean using standard deviation as the units. Okay. The formula for the z-score is the following. And it is zi is the z-score, and this is xi minus x bar divided by the standard deviation. And let's say we calculate this to be 2. This means for x3, I being 3. That means x3 is 2 standard deviations from the mean. If we said this is 3 for x4, that means x4 is 3 standard deviation from the mean. Okay. This zi can be greater than or less than or even equal to 0. Okay. If the z-score is less than 0, then the xi is less than the mean. If the z-score is equal to 0, then xi is equal to the mean. It's right there at the mean. And lastly, if zi is greater than 0, then xi is greater than the mean. So in these two examples, these are positive. So x3 is 2 standard deviations bigger than the mean, and then x4 is 3 standard deviations bigger than the mean. Okay. Okay. All right, so we're gonna use this to let's do an example 2.13. Clear this for all, and we're gonna do example 2.13. Suppose we had 2 students. They each took a college entrance exam, you know. One took the SAT and got 1440 out of 1600, while the other took the ACT and got 31 out of 36. Which student has performed better on the exam? Okay. So we go to, so to figure this out, we need to know the mean and the standard deviation. And let's suppose we found that out. For the SAT, the student got 1440. The mean was 1002 and the standard deviation is 168. For the ACT, the student got 31. The mean is 21. Standard deviation is 5.2. In both cases, the student did better than the mean. But did one do more better than the other? Let's find out. All right, to figure this out, let's calculate the z-score. For the z-score for the SAT student, that would be 1440 minus the mean, 102, divided by standard deviation, 168. And we calculate this to be 2.61. For the z-score for the person who took the ACT, it's 31 minus 21 divided by 5.2. And when we punch this in the calculator, we get 1.92. Excuse me. Okay. Okay. So what we see here is both of them are positive. Both SAT Z score for the SAT student and Z score for the ACT student are positive. So that means that both 1440 and 31 are higher than the mean. And we see that. We see that. The z-score for the SAT student is larger, meaning this is further away from the mean compared to this guy. Z-score for SAT is 2.61 standard deviations from the mean. For the ACT is 1.92. So because this is a bigger number, the SAT student is further out to the extreme or more further away from the mean, meaning this student did better than the ACT student. All right, let's move on and let's talk about percentiles and quartiles. Clear this? All right, what is a percentile? What is a quartile? Let's introduce percentile first. A percentile is another measure of relative standing, but z-score, it's how far you are from the mean. Percentile is where are you in the sense that how much bigger are you compared to the rest of the sample or population. Okay, for example, so let's say example, admission test scores of the college university are frequently reported in terms of percentiles, right? So if you're in the 99th percentile, that means you're better than 99% of the people who took the test. If you're the 54th percentile, that means you're better than 54% of the people who took the test. That's the kind of stuff we get when we when we took the SAT. You wanted to be really high up there. Okay. A set of n data points or measures on some variable x has been arranged from the smallest to the largest. The pth percentile is the value of x that is greater than p% of the data and is less than the remaining 100 minus p% of the data. Okay. So for example, if p is equal to 54%, that means that means this value, let's say P is 54%, is I don't know, a SAT score of 1040. Okay, that means this value of 1040 is better than 54% of the people who took it, but worse than the rest. Okay, rest of the people, 100 minus 54. Okay, all right. So let's suppose we want to know the location of the p percent in our data set. Okay. In our data. So we have a data and we want to know the location of the p percent. That formula is LP is equal to P divided by 100 times N plus 1. Okay. Okay. So how do we figure this out? And the next thing is from here is to figure out what is the value of that location. We could use that using the location of the p percent, and then from here we could calculate the value at LP. Okay, so that's what we're going to do now. I'm going to get some data, stick it into Excel. We're going to calculate the location of some p percentile, and then the value of that location. So let's do that in Excel. We're going to copy do the example on page 22. Okay. Okay, let's put in the data. We have 5710, 5880, 5880, 5920, 5950, 6130, 5755, 5880, 5890, 5940, 6050, and 6325. So this is the data we have, and it looks like it's ascending order. This is the smallest, second smallest, third, keeps going down, and this is the largest. So this is our data. I'm going to count to see how many we have. What is our N? This is equal to count all the numbers here. How many numbers do we have? Close parentheses. And we have 12. We have 12 data points here. All right. So from here, we want to find, they said in the example, calculate where the 80th percentile is. Okay. '80th percentile. Okay. So this is L80, I guess, right? LP, which is L80. And to figure this out, it's 80 divided by 100, okay, times N, which is 12, plus 1, close parenthesis. And they say the 80th location of the 80th percentile is 10.4. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 10th spot in ascending order, and this is the 11th spot, and this is the 12th spot. So it's in between 60, 50, and 61, 30. Okay, So we know it's 10.4. The 10th spot, that is equal to this. And it's 0.4 bigger than this guy, okay? And what you have to do is figure out, what do I mean by 0.4 bigger? Well, this is, we need to figure out the gap between this guy and this guy, which is 1630 minus 6050. That is the gap, is 80. That's the gap between the 10th spot and the 11th spot. And we're 40% of that gap away. So it's equal to 40% times this gap, 32. And then now we got to add these two together. So the 10.4th spot is equal to 6050 plus 32, which is 6082. That is the value at the 80th percentile. Okay. If we want to do something else, let's do a location. Let's do a different one. It's not here, but let's do another one. Location of 90th percent. Let's do 55th percentile, L55. And this would equal to 55 divided by 100 times n plus 1. So it's 7.15, 7.15. 1, 2, 3, 4, 5, 6, 7. I'll use a different color. And 8. So it's in between these two. Okay, so the 7th spot, is equal to this guy. And then 0.15 spot, this is equal to the distance. Well, first we got to figure out the distance. That is the distance between this guy and this guy. And then we got to multiply the distance times 0.5 is 3. So the 7.15 spot is equal to this number, the 7th spot plus 3, which is that number right there. The 5th location of the 55th percentile is 7.15, and the value is 5923. Again, the location of the 80th percentile is 10.4, and the value is 6082. All right, let's move on. Figure this. And now we're going to do quartiles. Okay. A set of n measurements on the variable x has been arranged from smallest to largest. So once you do that, the lower quartile, sometimes called the first quartile, or Q1, is the 25th percentile. The second quartile is the 50th percentile. It's also the median, what we've already learned about. The upper quartile, sometimes called the third quartile, or Q3, is the 75th percentile. There's also Q4, but no one cares. I mean, that's just the max, okay? That's just the max. Okay. Now let's give you the Excel formula for percentile and quartile. For percentile, it's the following. It is And the quartile is the following. All right, so this, if you plug these in, if you use these formula, you get the value associated with a specific percentile. So the percentile or quartile, it's percentile.exe, put in the data, comma, and what percentile are you looking for? The value of what percentile? If you put in, 55%, 55% or 0.55, you would get the value at the 55th percentile. Here, the quartile is quartile.exe. Put in the data and and then you put the quartile number, like 1, 2, 1. Second quartile is 2. Third quartile is 3 or 4. You would get the value at the 25th percentile, the 50th percentile, 75th percentile, or the 100th percentile. Okay, so let's do this. We will do this using Excel. Let's go back to Excel. Okay, so we put in the data. And let's say equal to percentile.exe. Put in the data. And put 80th percentile, close parentheses. We got the same number. So you don't have to look for it using this location and 10.4 and all that. You get it right there. Location at the 50th percentile, 55th percentile.exe. Stick in the data, comma, 55%. Get the same number. Okay, now let's do the Q1, Q2, Q3, Q4. So 25th percentile. This is the 25th percentile. This is 50th percentile. This is 75th percentile. And this is a 100th. I rarely do this one, so I don't know if this one will work. Let's try it. So one way of doing it is equal to percentile. Put in the data, comma, 25%. Another way is doing quartile.exe. Put in the data, comma, 1 for the first quartile. Same number. Oh, why is it the same number? Quartile. Should be the same number. Why isn't it the same number? Did I do something wrong? Oh, this should be the same number. I need to figure this out and get back to you. Okay. For the 50th percentile, it's percentile. Let me see this. Oh, you know why? Because I didn't do exe. I'm so sorry. .exe. There it is. I'm so sorry. I used the wrong formula. Percentile.exe. And then you get the same number. Okay. Percentile.exe. Put in the data, comma, 50%. Get the data. You get the number. Or you could do quartile.exe. Put in the data, 2. Or you could do median. Put in the data, close parentheses. Look, all the same. The third one, that's percentile.exe. Put in the data, 75%, close parentheses. Quartile.exe. Put in the data, 3. For the fourth quartile, hopefully this works, percentile.exe. Put in the data, 100%. Oh, it didn't work. Quartile.exe. put in the data, comma, 4. Yeah, it didn't work. Just stick with max. Apparently that doesn't work. So just stick with max. There. Okay. Fourth quartile is the point where 100% of the data is below. That should be the max. But yeah, it didn't work. Anyways, first, second, third quartile works. The other one doesn't work. All right, let's move on to whiteboard. And let's talk about the 5-number summary and the box plot. Clear this. 5-number summary and the box plot. All right, the 5-number summary is pretty straightforward. Let me put that up real quickly. This is the 5-number summary. Someone asks you for the 5-number summary. It's just the min, first quartile, median, third quartile, max. That's all it is. Okay. All right, let's move on to the box plot. Okay. Let me clear this. Box plot is it visually describes the data distribution, kind of like the relative frequency distribution does, but differently. It's a quick way of detecting skewness in the shape of the data. You could do that, but one thing you could do with the box plot is you could quickly identify outliers using a rule of thumb. Okay. So to construct the box plot, let me first just kind of show you what it looks like. And then I'll show you the step-by-step how to construct it. Okay, so you have the data. It's on the x-axis like this. You have the data. You're going to have a box. This lower portion of the box, that's Q1, or the lower quartile. The upper portion of the box right here, this is Q3, or the upper quartile. Okay, somewhere in here, you're going to draw a line. And this line is the second quartile, or the median. Okay. So this box provides the lower, the upper, and the median. All right. From here, we're going to calculate something called the interquartile range, IQR, which is equal to the interquartile range. And the interquartile range is just Q3 minus Q1, the value at Q3 minus the value at Q1. And that shows you the middle 50th, because this is 75 percentile. This is the 25 percentile. So the difference here is the middle 50th percent of data. Okay. And we're going to use that. Specifically, we're going to use that to build walls to identify outliers. Okay. So from the first quartile, we're going to go out 1.5 times IQR. And from the third quartile, we're going to add 1.5 times IQR. So the first quartile, we subtract 1.5 times IQR. The third quartile, we add 1.5 times IQR, and we'll build a wall. Okay, build a wall. And then we look at the data, we plot all of the data. And if you have some data point right here and some data point right here outside the walls, we're going to mark them with an asterisk. And we're going to call these outliers. Okay, and we're going to kill them off from the data. Once you kill off the outliers from the data, we're going to have new mins and new maxes that are not the outliers. And we're going to build a line up to, okay, this new min and the new max without the outliers. This is the classic box plot or box and whisker plot. Okay, I just kind of went through real quickly what it looks like and how to create it. So let me show you the step by step. Okay. Just write it out step by step. All right. Constructing the box whisker plots or the box plot. Calculate the median, the upper, lower quartile, and the IQR of the data set. Okay. Draw horizontal line to mark the data. Okay. And form a box just over the horizontal line. Okay. Where Q1 marks one edge of the box, Q3 marks the other edge of the box. You draw the box and draw a vertical line through the median or Q2. Okay. So here's the box with the median. Now we're going to draw these fences, the walls. In order to draw the walls, and why do we draw the walls? We're going to detect outliers. Okay. You draw the lower fence here. Okay. You calculate that using Q1, and you subtract 1.5 times the interquartile range, IQR. Why 1.5? Because some dude at Harvard said so. Some dude at Stanford probably says 2. Some dude at MIT probably says 1.58. This is a rule of thumb, so don't worry about it, okay? We're going to use 1.5 rule of thumb because that's what our book uses. The upper fence is drawn by using Q3, and you add 1.5 times IQR. Draw these walls or fences. Okay. Guess the fences are shown with broken lines. I use solid lines, whatever. I'm not going to mark off points for that if you did it. Any measurements beyond the upper and lower fence are considered outliers. We mark them with an asterisk. Mark any outliers with an asterisk. Draw horizontal lines called whiskers from the end of the boxes to the smallest and largest observations that are not outliers. So once you kill off the outliers, what is the new min and the new max? And you draw the whiskers to there. That's how you do this, okay? We are done with this chapter. Have a good night.